The specific yield will be an important property affecting the amount of water that can be stored in a porous material, and perhaps more importantly, the amount of water that can be released from storage from a porous material. And so to understand the meaning of specific yield, let's take a look at this experiment. And I'm showing over here a column of porous material that's saturated with water. So imagine a cylinder that we're looking at as a 2D slice, and it's filled up to the top. So this is akin to the water table being right up here at the top of the column. And then I'm going to go and open up a valve here at the bottom, and I'm going to let water drain out of the column. And so the water drains out, and the water table that starts out up here falls, and when that happens, water drains out and it accumulates in the cup. So let's see. There you go. You can see it happening here a little bit more slowly this time. Okay, so we've got this gravity drainage process going on and water that accumulates as a result of gravity drainage. Now, if you were to take a look at this porous material here, there'd still be some water trapped in there because capillary forces will be holding on to some of the water. And so we've drained some out, and we've got some retained within the porous medium. And that results in a couple of definitions. So the specific yield, this is the volume of water that would drain by gravity per total volume. So if we were to determine the specific yield from our experiment, it would be this volume of water that's come out as a ratio of this total volume of material that we've drained. Now, there's going to be some material, or there's going to be some water left in the pores, and so the volume of water retained during gravity drainage, I'm going to abbreviate it here, per total volume. That's called the specific retention. Okay, and I think that it's clear that if we start with pores that are saturated and we drain some of the water out of the pores, and then we have some volume retained in the pores, that if we do this, if we have volume drained over volume total plus volume retained over volume total, then if we add the volume drained and the volume retained, that's going to be the total volume of water over the volume total. Now this volume total here is the total volume of the porous media. If it's saturated, then this ratio just equals the porosity. So the specific yield plus the specific retention is equal to the porosity, the total porosity. Okay, so the total volume of the aquifer, total volume of water that has drained from the aquifer, we can determine that because we can say, well, specific yield equals volume drained over V total. Okay, well, the volume total, if we recognize that right up here, this is the water table, and the water table drops like that, so we can think of this as something like this. So the water table is dropping from there to there. This is a unit of area. So the volume total equals, and that's the change in head. So for a drop in the water table, the total volume of the region that has been drained is area divided by delta H. So specific yield is equal to the volume of water drained per area of the aquifer per drop in the water table. Okay, so this would be another way to think about the specific yield. And so this guy would say right like that. Okay, so this allows us then to equate the volume of water that has been released from storage due to a drop in the water table. Yeah, so there's some animations describing the water drained by gravity and the volume and then water retained by gravity. Okay, so let's see, we have this. We have the specific yield. This is going to be the volume released from storage, volume of water released from storage per total volume, which is per area per drop in the water table. Okay, so that would be what's happening for a situation like this. Here's just a representative block within the where there's a water table there, it drops to there, and that's delta H. And there's area. Okay, now we also might imagine that if we put water into this, say we start off with a situation like this, with the water table is here, and we add water, add some recharge, and the water level rises to here. Okay, so now we have an increase in the water level instead of a drop. Well, we might imagine that if we started at this level and then we dropped it down to here, we would give up a certain amount of water. And then if we added that water back, assuming everything is ideal, then the water level rises back to the same place. Okay, so we could also write this, that the specific yield is equal to the volume added per area per change in head. And we might, just to have it work out right, we might want to say this is drop and this is rise. Okay, so we get the signs to work out right. Okay, well, we also then should recognize that the recharge, if we have recharge being a flux, then it would be a volume that's added per area per time. So an annual recharge rate would be a volume of water that's added per unit area of the aquifer. So the recharge, say the annual recharge would be volume of water added per area of the aquifer. Okay, well, if that's okay, then we see right there that this ends up being recharge. Okay, so the specific yield for a recharge case would be, the specific yield would be the recharge divided by the change in the rise in the water table. Okay, so what we can do then is to say, well, that leads to this. The change in the water level, the rise in the water level due to recharge is equal to this. Okay, and what that means is that, let's say that let's say, around Clemson, we might expect to have, say, 6 inches of recharge in a year. So R is 6 inches. And so if that's the case, we might then be interested in how much would the water level in a well change. Well, if R is equal to 6 inches in a year, then the water level rise is clearly going to be not equal to that because we have the specific yield here. So we saw earlier on the previous slide that the specific yield plus the specific retention is equal to the porosity. So that means that the specific yield has to be less than the porosity. Okay, we saw values for porosity. They range from a percent or so up to maybe 50% for clays. And the specific yield will be less than that. So let's just say, if the specific yield were equal to, say, 0.2, then we would have a situation like this where this is 0.2, and that would be 5R. So the change in the water level would be 5 times greater than the recharge. So if we had this case where we had 6 inches of recharge in a year, then we might expect that would be equal to 5 times 6, 30 inches of water level rise in in a well that was tapping into the water table. Okay, so the water level would rise by 30 inches as a result of 6 inches in recharge. Okay, so that's an important point, that we'll always expect to have a larger rise in the water table, a rise in the water table that's larger than the amount of recharge because of the specific yield. Okay, so now I think that we should take a look at some of the values. So let's just reiterate: specific yield plus specific retention equals porosity. So this is the specific yield would be equal to the porosity minus the specific retention. Okay, so for gravel, we would expect the specific yield of this range, and these data are from this publication here. And so for gravel and coarse-grained sands, what we expect is that when they drain by gravity, that there's just a fairly small amount of water that's retained in a gravel. It's kind of coating the grains, and where the grains are in contact, you have a little bit of water in there. But the specific yield is probably fairly close to the porosity. So this is in the range of what we would expect for the porosity of a gravel. If we look at sands, we have similar range, and so medium grain sand up to gravel, 0.15 to 0.335 or so. And these are from laboratory measurements that were made on these various different materials. Now, as we start to get finer though, fine grained sand, silt, and clays, what we see is that I guess for fine grained sand, the high end is still about the same, but the low end is decreasing. And then when we go to silt, we have the specific yield can be really quite low for silt, 0.03, even though the porosity for a silt could be 0.2, 0.3 perhaps, but the specific yield is quite low because you have more water retained in the silt during gravity drainage. Okay, and then for clay, it's quite small. Remember, clay, we said porosity was 0.4 to 0.6, but the specific yield is 0 up to 0.05. So most of the water is going to be retained in clay during gravity drainage. Only a small amount is going to come out as a result of gravity. Okay, so these are some good values to keep in mind. So let's do an example. A rainstorm causes 1 inch of recharge in a clean, well-sorted sand. What kind of change in the water table elevation would we expect? Well, we said the specific yield was equal to the recharge times the change in height. So the change in height would be equal to the recharge divided by the specific yield. And the specific yield of clean, well-sorted sand, well, we go back. This is the data, and you can see that it's all of these are somewhat ranges, right? You're not going to be able to say for sure what it is if you only know that it's a clean, well-sorted sand. But if we look at these values, we might say, well, a reasonable value representative might be 0.2, kind of midway. So let's do that, and we'll say specific yield is 0.2. So this would just be equal to, if the recharge is 1 inch divided by 0.2, then we would expect the water level change to be 5 inches. Okay, so if we had a well like this, here's the ground surface, it rains, we got recharge reaching the water table, recharge of 1 inch, and that's going to be 1 inch cubed per 1 inch squared. That's what we mean by 1 inch of recharge. Then that will cause the water table to rise by 5 inches. Okay. All right. So that's the storage change, retention of water in porous media due to gravity drainage. Another type of porosity that we're interested in is the effective porosity, and this ends up being how we relate the flux to the velocity. So the effective porosity will be, we could, if we want to come up with a definition that is related to how we're thinking about porosity, then we would say it's the volume of pores that are important for flow to the total volume. Okay, so this is kind of vague. Volume of pores important to flow. We can see conceptually why we would have this, because remember back when we were looking at those CT scans of pores, that some pores are isolated from other pores, so they don't really contribute at all to the flow. Some might have, some might be dead end pores, so we might have a pore structure that looks like this. So the water would flow like this, but wouldn't really go into that pore during the flow process. So we can see why the pores that are important for flow might be less than the total pores, but just what this means is a little vague. But I think what we can see, well, here's the way it works. Effective porosity then is used to determine the velocity from the flux. So this is the way we think about it when we think about the meaning of porosity, but the way that effective porosity is used is to relate velocity to flux. Okay, so velocity, if we have like a tube here, velocity is the distance that a particle of water would travel in an increment of time, and the flux is the volumetric flow divided by this cross-sectional area and so they have different concepts, and the effective porosity relates those two. So we can think of effective porosity then as the flux in the x direction or in some direction divided by the velocity in that same direction. Okay, and indeed, if we then can measure what the flux is and measure the velocity, then we get, I think, a pretty clear definition for effective porosity, even though this definition here doesn't really have any mention of a ratio of pore sizes. Okay, so this definition here is getting a little bit different than what we've been saying porosity is, but nevertheless, this is based on the definition of the effective porosity. So here's a way to think about effective porosity. If we have flow going through this tube and the tube is filled with sand, then we've got an area here that is the total area that's defined by that area. And we would have an area that would allow the flow. And if we were to zoom in, on this, right in here, we would have some pores. And the area that would allow flow would be down in there, that the area between the pores. Okay, so the flux we can think of as a volumetric rate divided by the area total. So this area here, the velocity, the average velocity would be the volumetric flow divided by the area through which flow is occurring. So if there's no sand there and this is just a completely filled pipe, then the area of that allows flow is equal to the area, the total area, and the flux and the velocity are equal. But in this case where we have porous media, the area that allows flow is less than the total area. So this is less than that. So the velocity is greater than the flux. Okay, so we can do this. We can say that the just rewrite this, and I could write that like this. Okay, so this is like a chain rule, and this is the definition, and we just write it like this. And what we see then is that this right here, that's the average velocity, just from what we said here. And this is the ratio of the area to flow to the area total. And so now if I say, well, this area ratio, I'm going to say, well, I'm going to assume that the area that allows flow over the area total, if I'm going to assume this is equal to the volume that allows flow over the volume total. Okay, or we could say that's the volume of pores where the flow is important. And if that equals this, then we can say this is equal to the effective porosity. Okay, so this is equal to the effective porosity. And we get then the flux equals the average velocity times the effective porosity. Or the average velocity equals the flux divided by effective porosity. Okay, so that's how we got the relation that we gave on the previous page, and this is a way of thinking about it conceptually. We have to have this hold, and you can show for some certain geometry of pores that this is true. In general, though, it isn't necessarily true. But this then is the definition that we'll use for, well, yeah, if we bring the effective porosity over on the left side, that would be the definition of effective porosity, the ratio of the flux to the average velocity. Okay, so we'll also be interested in travel time, and this is the time that it takes for a particle of water to go from one point to another. And we'll be interested in this really for a variety of reasons. If we had a contaminant that was moving with the water, and we knew how long it takes the water to go from point A to point B, then that would be how long the contaminants would take. And some contaminants may move with water, some of them lag behind the water, but nevertheless, the time that it takes for water to go from point A to point B is going to be an important kind of basic measure of the groundwater system. So that's how we can use the average velocity. And so let's see, the average velocity, that's going to be the change in length over change in time. So here's delta L, there, that would be point A to point B, and we want to go from there to from A to B, and we'll have a certain amount of time that is required. So that travel time would just be equal to the distance that we need to go divided by the average velocity. And so if we the average velocity, then we can get from the flux divided by the effective porosity. And the flux, remember, we got from Darcy's law, that would be conductivity and times dH dl, and take all that divided by the effective porosity. Okay, so we find a way now to get the average velocity from the head gradient that we know how to measure. We need to be able to get the hydraulic conductivity, and if we have then the effective porosity, we can get what the average velocity is. Okay, so here's an example. The volumetric flux is given and effective porosity is this. How long does it take for the water to travel 100 meters? So we're going like this. There's one point A, another point B, 100 meters. The flux is equal to 0.05 meters per day. The velocity is the flux divided by the effective porosity, and that would be 0.05 meters per day by 0.1. This is dimensionless, so that looks like 5 meters per day. The velocity is the distance per time, and so the time is the distance divided by the velocity. If it's 100 meters divided by, there you go, half a meter a day. So 100 meters, and the velocity is 0.5 meters per day. Then we cancel out, we see the units are the result is days, and it's going to be 200 of them. So that's the travel time in this this particular example. Okay, so we've seen now a variety of different types of porosities, and one thing that they all have in common is that they are, well, that they are ratios of various different quantities. So the porosity is the ratio of the volume of the voids to the total volume, and we also might have the weight or the mass that we could determine for the total material and for the solids. And so this gives a variety of ratios that we can use. Here's the porosity, and that's the volume of the voids to the total volume. We can have a variety of other things where we include the mass, the ratio of the total mass to the total volume, would be the total bulk density or the wet density. We might have just the mass of the solids to the total volume. That's the bulk density or the dry bulk density. And let's see, here's another volume ratio. The porosity is the volume of the voids to the total volume. If we take the ratio of the volume of voids to the volume of the solids, that's the void ratio. And there are several others that are kind of related to porosity. The volumetric moisture content, that's the volume of water to the total volume. So if we compare that to the porosity, the volumetric moisture content would be equal to the porosity for saturated conditions. But where it's unsaturated, then the volumetric moisture content may be less than the porosity. The degree of saturation is another ratio where you take the volume of water in the soil to the volume of pores. And the air-filled porosity, the volume of the air in the pores to the total volume. Okay, so a variety of different porosities. This is a handout to kind of summarize these various different ratios. Also on the handout, there are some simple relationships between the different quantities. Here's the relationship between porosity and the void ratio. Okay, so some things that you should know that we've talked about over the last two videos. The factors controlling the primary and secondary porosity, this concept of representative elementary volume, some typical values of porosity, the specific yield, retention, and uses to determine the effect of change in water table, or basically the relationship between the change in the water table and the recharge. We could also have the change in the water table and the removal of water, say from pumping. And then we also looked at effective porosity, travel time, and the uses of those things.